In this video, we'll work through examples of calculations for a zero-order reaction using the linear form of the integrated rate law. For all of this work, I strongly recommend that you form the habit of solving for the variable of interest first, then plug in the numbers. This approach may be different than how you solve problems in a math class, but it's important here so that the units cancel as you go along and you can more easily keep track of the sig figs. We'll first take a look at half-life, and there are a couple of ways that you can go about this. Now, the problem here is obviously asking you to derive the equation for half-life. I think that is a really useful skill to be able to apply the algebra, so that way you can always figure out what that equation looks like. On the other hand, for the purposes of an exam, it might be easier for you to memorize the equations for zero, first, and second order half-life. I'm not a big fan of memorization, but the equations aren't that difficult, and so that is something that you may want to do. However, I'm going to say again, I think it's really, really important that you're able to extract the half-life formula out of the integrated rate law, and that's what we're going to do here. Whenever we derive an equation for half-life for any reaction order, there are two relationships that we need to set up first that are related to the definition of half-life. The first is that the concentration equals the initial concentration divided by 2. That is, it is equal to half of the original concentration. And the second one is that we set T equal to the half-life, or T equals T1 half. So we'll substitute these two equations into our linear form of the equation for zero order integrated rate law. So that is A equals minus KT plus A naught. We'll make the substitutions first and then clean it up. So for A, we have A naught over 2 equals negative K T1 half plus A naught. Because we have this plus right here, we need to make sure that we do that subtraction first as we're rearranging the equation. So we're going to subtract A naught from each side. That gives us A naught over 2 minus A naught equals minus KT1 half. The next step is to get a common denominator for our A naught term. So this first part stays the same, A naught over 2 minus 2 times A naught over 2. So we've just substituted in that common denominator, so that way we can do that subtraction pretty easily. This still equals negative KT1 half. So when we do this math on the left side, we end up with negative A naught over 2 equals minus KT1 half. We can cancel out those negative signs. That brings them both to plus. And then divide both sides by K. So the K will cancel over there. And we end up with T1 half equals A naught over 2K. Now this is just one way of rearranging the equation to isolate the T1 half term. It's fine if there's a different way or a different order of the derivation of the steps that works for you, but you should be able to apply the algebra to get to this equation for T1 half. Next, we're going to use that equation of T1 half to actually solve a problem. So let's just write that down first. So the equation that we're going to use is T1 half equals A naught over 2K. You'll notice in a lot of the work that I do, in cases where we have a term in the denominator that has units that span numerator and denominator, is that I will scoot that term over and write it as its own separate conversion factor. So that way we don't have any inverse units that we're trying to cancel. That's a place where a lot of mistakes are made. And you'll see what I mean by that as we start to work through the problem. It's also a really good idea to go through and identify your terms within the context of the problem. It only takes a few seconds, and it helps to ensure that you are getting the right values for the right variables. So in this case, our A naught is pretty clearly defined as A naught, so we don't really have to worry about that. And the same with our K, and we can go ahead and just plug those in. By the way, in this example, the 2 is exact, so we won't be considering it when we deal with our sig figs. Be very careful with the units, especially those units of K, because they often have numerator and denominator units, kind of like I was mentioning a little bit ago. Mathematically, this isn't difficult. Okay, so we have T1/2 equals A naught. Please, please, please write in the units. This is one thing that I see at the Chem 151 level, is that students will tend to not include the units and just plug in the numbers. Please make sure that you're including the units. Now, where you decide to put that 2 can go with either term. I think I will just go ahead and put it underneath the A naught. So now my K is in the denominator, so that means that I'll write it as 6.8 times 10 to the negative 4. The molarity goes with that value, and the seconds for K are inverse, and that means that those will flip to the top. When those seconds flip to the top, don't include the -1. We've already accounted for that by moving those units to the top. Taking a look at our sig figs, we have 3 sig figs for the molarity. As I mentioned, the 2 is exact, and 2 sig figs for K. So our final result will be reported with 2 sig figs. So when we do the math, 0.0596 divided by parentheses 2 times 6.8 times 10 to the negative 4 gives us 43.8. 2 sig figs will give us 44, and then make sure that you write the units, which are seconds. Let me go back and cancel the units. I didn't do that as I went along. My apologies, but molarity will cancel, and we're left with units of seconds. You've been canceling units ever since you were in Chem 101. Please make sure you still apply that skill here, because T1/2 has to have units of time. And if you end up with something like molarity squared over seconds, that's not a unit of time, and that immediately tells you that there's something upside down, something's not quite right with how the equation was set up. Our next example is a good one because it does require us, I think, to go through and identify our terms. And as I mentioned in the last example, this is something that you really want to make sure you're doing with any kind of problem, not just these integrated rate laws. Go through and define what is it you're trying to figure out, what are you trying to calculate, and what do you already know. So we're asked to calculate the concentration of A. Right? We don't know that. After some molarity of A reacts, so that has to be our initial concentration, reacts for a time of 25 seconds. And we're also given K. So we have A naught, T, and K, and we're trying to solve for A. This is still a zero order reaction. Let me just mention, this whole problem set, this whole video is based on zero order reactions, and that was stated at the very beginning. If this had been an isolated problem and we didn't have all that information at the very beginning, I should tell you that it is a zero order reaction. However, because you're given the rate constant, you can figure out that this is zero order based on the units of rate constant. So if you go back and take a look at the videos, the two videos where we looked at the linear forms of the integrated rate law and how those connected to the linear plots, we looked at the units of k for each of those situations. And so this is one more way that you can tell what order the reaction is. So we're going to follow the advice that I gave earlier, which is we start with the linear equation and we rearrange it, if needed, to solve for the variable of interest. So our linear equation is A equals minus KT plus A naught. And the truth is, the more you write the linear equation, sort of that repeated, practice with it, the more you really do just start to internalize it and learn it. And I think that makes a lot of these problems a lot easier. So that's another reason why I prefer that. In this case, we are solving for A, which is right here, and our equation is already set up for us to do that calculation directly. So we don't need to rearrange it. Again, I caution you, be careful as you enter the values in, because mathematically it's pretty simple, but it's keeping track of the sig figs and the units that tends to be just a little bit tricky. So we have A minus KT. I'm going to write K out as a full expansion, numerator to denominator. Don't forget the negative sign. I find that that's something that I tend to do here and there. So just be aware of that. So it's 5.29 times 10 to the negative 3. Molarity goes in the numerator divided by seconds. So that goes in the denominator. This is a multiplication times time. So 25.0 seconds. Seconds will cancel, and this term has units of molarity. Don't forget, though, that we have to add the second part, which is 0.303 molar. So a couple of comments here. Whatever the units are for this term have to be the same after you cancel as the units in this term. And they are. We have units of molarity because seconds canceled, and we have units of molarity because that's just what we had. The other part that can be a little bit confusing here is dealing with the sig figs, because we have mixed math operations. We have multiplication and addition. So this multiplication will give us 3 sig figs and 3 sig figs. So when we multiply those together, we need to end up with 3 sig figs. But then we're taking whatever that value is, we're looking at how many decimal places corresponds to 3 sig figs, and then recognizing that we need to account for the fewest number of decimal places. So while it's easy enough to just plug all this into the calculator, you do want to keep track of the intermediate calculations, at least for the purposes of sig figs. So when I do this math, 5.29 times 10 to the negative 3 times 25.0, my value, and the negative, my value is negative 0.13225. That's just what comes out of the calculator. I need to keep 3 sig figs, so that's going to be here, and that also corresponds to 3 decimal places. Now it turns out, for this particular example, that my decimal places are the same, 3 decimal places, 3 decimal places, and so my final answer will have to retain 3 decimal places. So that last step involves the addition of negative 0.132 plus 0.303, and that gives me my final answer of 0.171. Don't forget the units, so we end up with the concentration of A is 0.171 molar. All right, in our next example, we're going to go through, just like we did previously, we're going to assign the terms, we're going to figure out what it is we're trying to calculate, and then rearrange the equation to allow us to set up the problem. The question reads, how many hours, that's a time, so that's what we're trying to calculate, does it take for the concentration of A to decrease from 0.1001, so that's going to be our A naught, that's the initial concentration, to some other molarity at this time, which will be the concentration of A, and we're given our rate constant. One thing that you want to notice here is that the question is asking for time in hours, but the time term of our rate constant is in minutes. You have to have those aligned. They have to be the same. So at some point, you're going to have to do a conversion to get from minutes to hours. So we start with our linear form, the regular linear form. A equals negative KT plus A naught. I know we really just want to plug in the numbers, but we're going to rearrange. So we are solving for T. That means that we have to get the KT term by itself. And just like a previous example, because we have that plus there, the first step is to subtract the A naught. So we have A minus A naught equals minus KT. We're solving for T, so we divide by negative K, and that's going to give us our time isolated. One thing you want to be very, very careful about, I know this is like the 14th thing that I've said to be very careful about, but it's true. Make sure that you are using parentheses in your calculator when you enter the values in the numerator, or push enter after you've done that subtraction. Otherwise, often the calculator thinks that you're taking A naught and dividing it by negative K, just that part, and it will give you a number that doesn't make any sense at all. So this is the form of the equation that we're using, and we're going to go ahead and plug in the values with units. Couple of comments that I mentioned earlier apply here as well. That is, you've got a subtraction in the numerator, so we've got to keep track of decimal places first in the numerator, and then our second part of the calculation is the division. Then we turn those decimal places into sig figs, number of sig figs, and then we can apply that final rule of division. And then the other thing is we've got K in the denominator, so I think it really helps to scoot that over as its own term, so that way you have clear numerator, clear denominator for the units, and the cancellation is just much easier. So we've got, again, these couple of extra things that we have to deal with, even though the math itself is not that complicated. So for our numerator, we have A, which is 0.0725 molar, A naught, 0.1001 molar, and K, negative K, is in the denominator, so negative 7.3 times 10 to the negative 5 molar in the denominator, and then the minutes flip to the top, so molarity per minute. We're going to take a look at what the sig figs, how those should work out for that first subtraction. Because it's a subtraction, we count number of decimal places. Our first value has 4 decimal places. Our second value also has 4 decimal places. And so when we do this math, 0.0725 minus 0.1001, we get negative 0.0276 molar, which comes out of the calculator, and it turns out that that is 4 decimal places. That's what we need. But now that we're going to use that in this multiplication division step, we have to count how many sig figs that corresponds to. And those 4 decimal places equals 3 sig figs. And then we'll apply that next step. So we have minutes at the top, negative 7.3 times 10 to the negative 5 molar at the bottom. Molarity will cancel. We're left with units of time in minutes, but we need to do that conversion for this particular problem. So we have 60 minutes in the denominator. That way minutes will cancel, equals 1 hour in the numerator. Looking at the rest of our sig figs, so we already have 3 for the first term. We have 2 for the second term, and these time conversions are all exact. So our final result needs to have 2 sig figs. So when we do this math, we have negative 0.0276 divided by parentheses negative 7.3 times 10 to the minus 5 times 60, and that gives us 6.3 hours. And our final example, we'll go through and assign our terms. So we have the concentration of A was measured at 0.0461 molar, so that's our A. After a certain time, 7.50 minutes had passed, calculate its original molarity, so that's our A naught, when the experiment started. And we're given K. Related to what we saw in the last example, we do have to make sure that our time units are consistent. In this case, they are. We have minutes and minutes, so there's no further conversion that's necessary. So we'll write our original linear equation, A equals negative KT plus A naught. We're solving for A naught, so we need to move the KT term to the other side. Because it's a negative, we need to add KT to each side. So we have A plus KT equals A naught. So plugging the numbers in, we have A naught equals 0.0461 molar plus the KT term. So just like the previous examples, I'm going to expand the units of K to make sure that they are present in a clear numerator and clear denominator. 1.2 times 10 to the negative 2 molar divided by minutes times the T term, which is 7.50 minutes. So we'll take a look at the sig figs for the KT term. We have 2 sig figs for K, 3 for time. So when we do this math, we need to end up with 2 sig figs. So A naught equals 0.0461 molar. This is an addition step. So at this point, we're keeping track of decimal places. So I'll just go ahead and write that down, that this is 4 decimal places. And we'll see what our KT term ends up having in terms of sig figs and what that means for decimal places. So when we do the math for KT, it's 1.2 times 10 to the negative 2 times 7.50. And the calculator gives us 0.09. But we need to turn that into 2 sig figs, so it will be 0.090. The units of minutes cancel, and so we have units of molarity, which is what we need. So as I've reported it, 0.090, that's 2 sig figs, but now we need to think about what that means in decimal places, and it is 3 decimal places. So when we do the math, our final result needs to be rounded to 3 decimal places. So doing the math, we have 0.0461 plus 0.090 gives us 0.136, and that's 3 decimal places, and the units are molarity.